talk, you have to prove one theorem in the talk. And
More than enough.
So that that's right, would be more than enough. But when you give a history talk, the usual way of giving a history talk is to write the talk, and then I read it to you. And so I'm going to give you a history talk today. As you can see, I'm not a mathematician because I'm wearing a tie. That's right. It's very dangerous. You're wearing a tie. And so this will be a little bit different for you, and a little bit different for me too. But as I say, I will also prove a theorem in this talk. So let me. The desk is up there, but that's too far away, and I need some light, so I'll just stand here. I hope you don't mind me holding the pages. So, the history of algebraic topology is not so easy to describe. It's a hybrid subject, and its roots lie in different places, and the synthesis of these diverse areas gave birth to the activity. It's also the case that the field of study, algebraic topology, only came to be in a time when branches of mathematics separated themselves into different communities. This separation is not a feature of earlier times in mathematics. It's also the case that the development of algebraic topology can be said to be one of the most impressive features of 20th century mathematics. So, to frame the history, let's consider some of the ways in which the 20th century had a different mathematics than other times. One feature of this is the rise in abstraction, which was pioneered by Hilbert and his co-workers in Göttingen. This approach to developing mathematics was much admired and emulated around the world. Eventually, topological notions were organized in this abstract manner. Second feature is that there were new centers of activity growing up into what you might call schools of mathematics, although this term should be used with caution. The spread of pioneering ideas often came from these centers outward, and so examining them is important. The third feature is that most history of mathematics is presented as a series of successes. What about the failures? Topology didn't simply spring forth in its present form, and some of the paths introduced were less successful and hence abandoned, sometimes actually to be taken up again later. A deeper presentation of history must include these failures and the contexts in which they occur. In a recent book on the development of contemporary mathematics called Plato's Ghost, Jeremy Gray identified a feature of mathematics early in the 20th century. The end of the 19th century is marked by what he calls, quote, a growing appreciation of error, unquote, especially in the developments in analysis and in the foundations of mathematics. There was a sense of anxiety that was evident, and the role of this anxiety was to foster, for example, a deeper desire for rigor. Anxiety about methods and results were not the only expression of fear as well. There was also anxiety about the status of this emerging field of topological investigation. I want to recount 3 incidents that reveal a kind of anxiety over algebraic topology. The first is from a recent article of Benno Ekman, who was a student of Heinz Hopf, and he recalled an encounter he had with Hermann Weyl. Ekman asked Weyl why he had published 2 papers in 1923-24 called Analysis Situs Combinatorio in the Revista Matematica Hispanico-Americana in Spanish. Weyl replied, that he did not want to draw attention to the publication, that his colleagues should not read them, and that the subject matter was not serious mathematics. Another remark on topology from the 20s is contained in a 1929 address to the German Mathematical Society by van der Waerden. He described combinatorial topology as, quote, a battlefield of differing methods, unquote. The lack of rigorous definition of manifold was a key issue here, and van der Waerden, who was a quintessential Göttinger mathematician, wanted clarity in this endeavor. The third incident that I want to mention, I learned through doing some archive work in Zurich, and it deals with Hopf and Alexandrov. A key figure in the emergence of algebraic topology is L.E.J. Brouwer, whose charismatic nature and leadership ability made him a guru to young topologists, as well as a threat to other leadership figures. Though Brouwer's work in topology was limited to the remarkable years of 1909 to 1912, he kept a hand in the field by encouraging others, and through his prominence as cooperating editor of the Mathematische Annalen from 1915. The Annalen was based in Göttingen and had become the most prestigious journal in mathematics in the years around the First World War. Its principal editors were Hilbert, Einstein, Blumenthal, and Cara Theodori. Brouwer was listed among the cooperating editors. When Brouwer's intuitionistic stance on mathematics threatened Hilbert's leadership on foundational issues, Hilbert requested the removal of Brouwer from the position of editor for the Annalen. Brouwer reacted with a flurry of irate letters, but eventually he withdrew from the Annalen. He then founded a new journal, Compositio Mathematicae. In their correspondence, the young topologists at the time, Hopf and Alexandrov, discussed this conflict with considerable interest. Hopf felt that Brouwer's absence from the editorial board would make it less likely that his papers, and papers in topology more generally, would appear in the journal, which drew the most attention in the mathematical community. Alexandrov felt that Hopf's work and reputation had reached such a stage in 1929 that he could publish anywhere. However, Hopf's next paper was submitted to Krelle's journal, and after his arrival in Zurich in 1931, his work appeared primarily in Commentaria Mathematica Helvetica, or Brouwer's journal Compositio Mathematicae. So he did in fact act on this feeling about Brouwer. In what follows, we'll relate these stories to the emergence of a new field in the 20th century. Along the way, we'll present some of the context that made the path to the study of algebraic topology possible. This talk's based on accounts of the history of these ideas, notably by Erhard Schultz and Moritz Eppel. And I also did some archive work in Zurich and Paris and elsewhere that supports some of the stories that I'll tell. So in the beginning of the talk, I want to tell you something that indicates that, as I put it, all roads lead from Poincaré. In a series of memoirs on the global properties of solution curves to differential equations on orientable surfaces, Poincaré introduced some topological notions relating the Euler characteristic of a surface and the behavior of singularities of a flow on the surface. To understand his definition of the index of a singularity of a flow on a surface, we'll consider now I can be a mathematician. Maybe I should take my tie off. To understand what Poincaré did, I want to consider just a piece of a surface. And on this surface, let me look at a curve that's closed and which is simply connected, meaning that I could draw this curve down to a point while it's looking at the surface. So for such a thing is called a cycle in Poincaré's language. And so what one has to imagine here is that there is on the surface a flow which is maybe determined by it's a flow is determined by some differential equation. And so if you have such a flow, these are the integral curves of the differential equation, then Poincaré associated to such a cycle an index. So this is the index which he introduced. It's made up of two numbers, and these numbers are determined by the following phenomenon. If the curve in the flow is tangent to a cycle at a point, then you count that as an exterior point. If the flow is tangent to the cycle by a curve that remains in the interior of the cycle, then you count that as an interior point. And so you count up the number of exterior points, you subtract the number of interior points, you subtract 2 and divide that number by 2. And this is what the index which Poincaré introduced to a cycle. He goes on in this paper, which by the way was published in 1885 and constitutes some of the work which he did in his PhD thesis, which places it fully 10 years before the famous topology papers of Poincaré. So it's interesting to think about this work as sort of the precursor to topology. Poincaré proves the following fact. Suppose I have a cycle which I think of as being built out of 2 cycles. So in other words, I take 2 cycles and I glue them together along one edge. So I have cycle 1, cycle 2, and I want to look at the sum of these 2 cycles and look at their index. And I want to think of the sum of these 2 cycles as the cycle which is obtained by ignoring the line of intersection. And so Poincaré proves that his index satisfies this property, that the index for the sum of the cycles is the sum of the indices. So let me make the argument that in fact this holds. Notice, for example, if I have an interior point for cycle 1, then that interior point represents an exterior point for cycle 2, and so in this sum they will cancel each other out. Hence, anything that comes from this line will be irrelevant. What's important, however, to think about is the 2 endpoints of the line, because, for example, I could have something like this happen. Notice that if such a line comes through like this, it's counted by the cycle on the left as an exterior point, but in the big cycle, it's not counted at all because it's transverse there. Likewise, I could have such a thing as this happening. In fact, there are other cases to think about. I could have it be tangent here and transverse there. Or worst of all, I could have this be tangent at both places. Well, the way to understand why these don't present any problem to our additive form here is to realize that when I add these together, here I'll have some count like this plus a count like this, and of course this is this. And what's odd about this, of course, is that number 4 sticking out here. Well, in this case, notice that I have 2 exterior points being counted, which are not counted in the big cycle. And so the 4 is 2 too many, and that 2 accounts for those 2 extraneous exterior points. Likewise, if I go over here and I count, this will count as 1 extraneous exterior, and here I will have an exterior point that's counted twice. So I'll have 1 and 1, and that accounts for the getting rid of the 2. And likewise here I'll have 2 exterior points which are being counted twice. Once again, I've overcounted by 2, and so this 4 fits in beautifully in order to remove the 2 extraneous counts. So we have a beautiful formula from a very odd-looking expression for an index. The way Poincaré then proceeds is to think globally about the surface. And so if I take a surface which is compact, then such a thing, for example, as a torus or a sphere, Poincaré then says, triangulate your surface by small triangles, small enough that you are able to know that each piece is a cycle. Now it's possible then to triangulate. I can form the sum of the index of all the cycles. And here's where the global properties of the surface enter into the picture. So let's see if I can do this count correctly. So this will be half of the exterior minus the interior minus 2. So let me count the sum of the exterior minus the interior first. Here's what I claim. I claim that no contribution is given by an edge, because if I have a surface which is closed, and then all of these triangles meet up and share an edge. And of course, if I have an interior point to one, it's an exterior point to another, and in the sum, they cancel each other. So that means that in this large sum, I am no longer interested in counting up these interior and exteriors, but I only am interested in what happens at a vertex. At a vertex, the flow is multimedia. It's a high use of technology here. But if I have a flow line passing through a vertex, then notice that flow line will be exterior to all but two of the cycles that meet. The reason, of course, is that it's interior as it comes in, interior, or it's on the inside, and so it's exterior to everybody it doesn't belong to. So this will be equal to, this sum will be equal to the valence, here counted up over the vertices, minus 2 for each vertex. Is valence the correct word for graph theory? The number of edges that occur at a point? Of course, if I count up the valence over all vertices, then of course that's equal to twice the number of edges. And so this sum becomes now twice the number of edges minus twice the number of vertices from the minus 2. So let's see, if I put this together with what I have over here for the cycles, this becomes 1/2 twice the number of edges minus twice the number of vertices minus twice the number of faces, where each face is what's surrounded by the cycles. And you'll recognize here that this is exactly equal to minus the Euler characteristic of the surface. So this is the proof that Poincaré gave, and he immediately understood that the Euler characteristic was forcing things to happen because of the surface. So for example, on a sphere where the Euler characteristic will be 2, that means that there must be singular points in the flow. Let's think about why that's true. If I take a cycle that's conservative, notice that it's just passing through without any singularities. It will contribute 2 exterior points and no interior points, and hence it will have an index equal to 0. So if all of the flow looked like this everywhere, if the wind were blowing in a non-zero way everywhere on the sphere, then the Euler characteristic of the sphere would be 0, which it isn't. So somewhere the wind is not blowing. So Poincaré made all of these deductions in this third part of his memoir on these kinds of curves, and it indicates very much a sense of the combinatorial nature of arguments that he could make, as well as an interest in surfaces and eventually manifolds in general, and the way in which their topology, what eventually becomes their topology, influences the behavior of mathematical systems on such objects. So this is 1885. I think I should put a picture up of our hero. And you can turn those lights off. Thank you. In his celebrated paper, Analysis Cetus and its supplements, Poincaré initiated the topological study of manifolds. He gave examples in various ways, as, for example, the inverse image of a regular value of a differentiable function that is x squared plus y squared plus z squared equals 1, for example. It gives a sphere. As a set with a finite atlas of parameterizations. In this case, he was thinking of analytic continuation of coordinates. As a geometric complex made out of simplices, just like he triangulated his surfaces here. You could do that in higher dimensions. And even more generally, as a cell complex made by identifying handle bodies along their boundaries, the so-called Haggard decompositions. Poincaré did not unify these examples with a single definition, as was his style. However, he did introduce new topological methods of study, including the so-called notions of cobordism, homology, the fundamental group. He introduced a notion of the equivalence of manifolds, what he called homeomorphisms, which are given by changes of coordinates, what we would call presently a diffeomorphism. And by collecting all such homeomorphisms into a group, Poincaré related this group implicitly to the generalized notions of symmetry found in Klein's airline program. Thus, Analysis Cetus, or topology, was a branch of geometry. He went on to prove the homological property of Poincaré duality for compact closed and orientable manifolds, and he posed the problem of generalizing the success of 19th century geometers to classifying surfaces in higher dimensions, that is, classifying manifolds. Of course, these proposed the so-called Poincaré conjecture. From the outset, the importance of having a sharp definition of manifold was clear. David Hilbert sought an axiomatic characterization of the plane as a manifold in his researches on the foundations of geometry. Hilbert's basic notion was that of neighborhoods, and this idea was refined by Hermann Weyl in his book of 1913 on Riemann surfaces. Weyl's definition of a two-dimensional manifold is based on a system of neighborhoods, at least one for each point, with each neighborhood being homeomorphic to an open set of the plane. After the development of general topological spaces in 1914 by Felix Hausdorff, the role of neighborhood systems and separation assumptions were made precise, and Weyl later added separation conditions to his axioms. The combinatorial definition of a manifold was the foundation for a 1907 article of Max Dane and Paul Haggard for Klein's Encyclopedia of Mathematical Sciences in the entry on Analysis Cetus. They took as basic the abstract data that describes a triangulation, the cells and their gluing data. And they discussed the questions of Poincaré, whether such a scheme was realized by a manifold, and whether two manifolds with the same abstract scheme needed to be homeomorphic, for which they introduced a notion of combinatorial equivalence via mappings between such schemes. Later, Steinitz and Tietze independently posed the so-called Hauptvermutung, the main conjecture for manifolds. Do two triangulations of a manifold have a common refinement? Or more generally, does in fact a compact manifold always have a triangulation? In higher dimensions, without a common definition for manifold, the study of manifolds was fraught with difficulties. as expressed by van der Waerden in that quote of it being a battlefield of different methods. The development of a theory of manifolds may be characterized as a response to two impulses after Poincaré. The first impulse was the computation of the new invariants, and this favored the combinatorial description of manifolds. The second impulse sought new examples, especially of three manifolds, in the hope of resolution of the Poincaré conjecture. An axiomatic description of manifolds was finally achieved by Veblen and Whitehead. In short order, Whitney was able to show that differentiable manifolds were identifiable with subsets of Euclidean space, and so a degree of intuition was returned to the study of manifolds by that result. Next, I want to discuss L.E.J. Brouwer and his role in the beginnings of algebraic topology. In the beginning of the 20th century, certain basic topological questions remained unsolved, among which were among the most important were Hilbert's fifth problem, which asks whether a continuous group of transformations of a manifold made a Lie group. The question of the topological invariance of dimension, that is the dimension of Euclidean space, a topological feature of that space, and the so-called Jordan curve theorem. Motivated by philosophical interests in the foundation of geometry, Brouwer began to work on Hilbert's fifth problem, which led him to a study of methods of topology. In particular, he immersed himself in the work of Arthur Schoenflies on the topology of the plane. Brouwer's penetrating critical faculties quickly spotted flaws in Schoenflies' work, leading him away from the fifth problem to questions about the foundations of topology. His investigation of mappings of surfaces led him to the first fixed point theorem, a continuous orientation-preserving mapping of the two-sphere to itself must have a fixed point. Around this time, he also proved, using Schoenflies' methods, that a continuous vector field on a two-sphere must have a singular point. This is an improvement of the Poincaré index theorem to continuous situations. So one can sort of see that Brouwer is trying to think very topological, thinking only about continuous mappings rather than using differentiable methods at all. Brouwer stated of these two new results of his, at first sight, one might even suppose they can be directly deduced out of each other. For those of you who have had topology, in fact, you know that's the case. The conundrum of their connection prompted Brouwer to write to Jacques Adamard, who suggested that Brouwer study Poincaré's memoirs on flows on surfaces. During a visit to Paris over Christmas 1909, Brouwer kept a notebook in which he sketched a definition of Poincaré's index of a mapping in a combinatorial setting. This led to a proof of the invariance of dimension. And with that, Brouwer opened up a new landscape for combinatorial topology. In particular, up to this point, focus was on the combinatorial representation of objects like manifolds. Representatives for homology classes in a manifold, and relations that determined the fundamental group from the combinatorial structure. Brouwer introduced methods that made any continuous mapping between two such objects representable up to deformation by combinatorial data, allowing the focus to shift from objects to mappings between them. A characteristic example of this is Brouwer's proof of the topological invariance of dimension. In this case, he studied whether there was a mapping from an n cubed to an m cubed that could be a homeomorphism. By breaking the n cube up into pieces and the m cube up into pieces, he refined this decomposition in such a way that it was approximated by linear mappings. And then what he did was define the degree of a mapping to be the integer p minus q, where p is the number of points in the preimage of a generic point for which the orientation is preserved, and q is the number of points in the preimage for which the orientation is reversed. Brouwer then showed that if you deform a map slightly, what we would call a homotopy of the map, the index, this degree of the mapping was unchanged. And so he was able to use this to describe the invariant of the mapping. Brouwer developed this mapping degree further to prove fixed point theorems about mappings of spheres. And he was able to use an index 1 kind of argument to show that the invariance of dimensions in this case. I know why that looks funny. It's the previous page. Finally, developing these methods, he was able to show that a continuous function from an n ball to an n ball must have a fixed point, and that's perhaps his most well-known theorem, the Brouwer fixed point theorem. The manner in which he proved this used the degree of a mapping. It used only the continuity of the mapping, and it very much introduced the use of simplicial approximation as a foundation for topology. Though Brouwer's contributions were viewed with respect, they were acknowledged as difficult to understand, and so he did not immediately attract a following to his ideas. So the next player in this discussion is McCleary. Brouwer published his new approach to topology in the years 1910 to about 1913, after which he contributed little to the subject. His work on invariance of dimension led him to an interest in a topological theory of dimension that was eventually developed by Pavel Eurozone and Carl Menger. Eurozone's work in the early 20s so interested Brouwer that he invited researchers in topology to visit him in Amsterdam. Among the visitors were Eurozone, Menger, Alexandrov, Viatoris, and later Jurevich and Freudenthal, who were his assistants. In December 1925, the eminent Göttinger algebraist Emmy Noether visited Blaricum, Brouwer's vacation home, and the group of mathematicians around Brouwer. At dinner in her honor at Brouwer's, she explained how the numerical invariants of combinatorial topology were better organized as the invariants of groups, so-called Betty groups. The dinner party included Alexandrov and Viatoris, and the first papers, which were to use homology groups, were written by Viatoris and by Heinz Hopf. Picture up there. No, homology was used before then, but it didn't mean the same thing. But in Viatoris's papers and in Hopf's papers, homology was a system of groups. You should note the years that Viatoris lived. They asked the question whether topology keeps you young. In his work, Vietoris extended the simplicial homology theory of Dane and Hagar and Poincaré in two novel ways. The first was in applying Noether's suggestion to use groups instead of numerical invariants. He worked mod 2 and defined an addition on cycles, calling the group of dimension n cycles as the nth connectedness group, and the maximum number of independent cycles as the nth connectedness number. This permitted Vietoris to argue with matrices with coefficients in the integers mod 2. The second extension was to a wider class of spaces, namely compact metric spaces. The main objects of study, manifolds, are often compact metric spaces, and the Hauptvermutung pointed out a possible gap between the combinatorial representation of a manifold as a complex and its topological nature as a space. In Vietoris's work, the notion of an epsilon complex was introduced for all epsilon greater than 0. If X is a compact metric space, then a combinatorial P simplex in X is a choice of P plus 1 points in X, and if such a choice has diameter less than or equal to epsilon, then it's allowed as a generator of the P chains on X. Vietoris showed that Veblen and Alexander's mod 2 homology groups for a finite Euclidean complex coincided with these groups using the epsilon complex. The second paper was by Hopp, who had learned of Noether's algebraic suggestion from his friendship with Alexandrov and his time spent in Göttingen. Hopp had mastered Brouwer's methods in his thesis and Habilitationsschrift, in which, among other things, he extended Brouwer's results on homotopy classes of mappings between manifolds. In his 1928 paper, he proved an extension of the Euler-Poincaré formula and used this formalism of homology groups in the framework of modules over a ring. Simplices of a geometric complex form the generators of a free module, and the kernel of the boundary homomorphism modulo the image gives the homology group as a quotient group. Using this formalism, Hopp gave an elegant proof of Lefschetz's fixed point theorem, and he also extended the range of homology theory by considering any cell complex without the assumption that it was a manifold. The extent to which homology might be used as a tool to study spaces other than manifolds was a theme motivated by the lack of success in avoiding the use of triangulations, and because the properties of general topological spaces were being developed in parallel to the development of combinatorial ideas. Alexandrov, Hopp's friend, Alexandrov advanced a general theory for compact spaces that lay between the ideas of Vietoris for compact metric spaces and Hopp for geometric complexes. He defined the notion of the nerve of a covering, which consists of an abstract cell complex whose vertices consisted of open sets in a covering and whose P simplices were collections of these open sets that had non-empty intersection. By taking finer coverings of a space, the homology of this abstract cell complex is seen to converge to a common set of generators, giving the notion of Betty numbers for a space. For compact manifolds, this agreed with the usual Betty numbers. The Czech mathematician Edward Čech considered the collection of all finite open coverings and was able to develop another homology theory in which the inverse limit of such a system of groups would be taken to be the homology group of the space. And in this framework, he was able to give new proofs of Poincaré and Alexander duality theorems. It's interesting to contrast the fate of these papers of Hopf and Vietoris that have the first mention of homology groups. Vietoris' paper is abstract, self-contained, and extends methods for internal goals, whereas Hopf's paper looked out to other areas of mathematics, algebra and geometry, for its goals, connecting with true and tried results from a new viewpoint. Vietoris' paper did not obtain much interest in the intervening years, but lately there has been some interest in epsilon homology again, and several efforts to apply topology. So you should see the work of Gunnar Carlson and Bob Greist for this appearance. In section 12 of Analysis Cetus, Poincaré associated a group of substitutions. Groups of substitutions were what you called a group in those days, to a manifold. And the way he did this was by taking small loops in the manifold and by simply running one loop after the other, he obtained a multiplication. And by taking loops to be equivalent, if one can be deformed into another inside the manifold, then you obtain, in this manner, the fundamental group of the manifold. To compute the group associated to a manifold, Poincaré defines certain fundamental loops for which any other loop is equivalent to the sum of multiples of these loops. I should point out, by the way, that this idea of deforming loops and counting only the equivalence class of these was motivated by complex integration, where if you take a line integral in the complex plane, only the singularities that are contained within the loop matter. And so these, what's that? For contour integrals. And so Poincaré was once again coming from an analysis point of view. The primary application of the fundamental group for which Poincaré was interested is to act as an invariant of manifolds. In the 1892 Compte Rendu announcement preceding Analysis Cetus, he posed the problem of classifying manifolds of dimension greater than 2 through their Betti numbers, and showed that the fundamental group was able to distinguish between 2-3 manifolds which both had the same Betti numbers, showing that the Betti numbers were not a sufficient invariant. The construction of 3 manifolds given by Poincaré was inspired by his interest in complex function theory, and the method of Riemann surfaces led Poincaré to use the universal covering space of a manifold for computations. This space is simply connected, and any loop in a manifold can be lifted to it. Any null homotopic lift goes to a closed loop in the universal cover. The equivalent curves lift to curves sharing the same endpoints. The permutations of the points corresponding to a single point correspond to lifts of loops, and hence gives a permutation representation of the fundamental group. Since abstract groups were not part of the mathematical canon at the time, this permutation representation was important to the transmission of the idea, and it made the universal cover a tool in the development. The equivalence relation among loops is what we call homotopy now, but the term homotopy first appeared in the 1907 Encyclopedia article of Dane and Hagar. The meaning is different than the present usage, however, because their term homotope means homeomorphic. The rigid structure of a cell complex is transformed in Dane and Hagar's sense of homotopy by moving vertices to vertices, edges to edges, etc. Transformation is the focus of the definition. It was Brouwer who made explicit the idea of homotopy. And in this framework, the role of simplicial approximation can be further appreciated. Concepts like the mapping degree shown to be a homotopy invariant of the mapping. Hopf showed that the mapping degree of a continuous mapping of the n-dimensional sphere to itself completely characterized its homotopy class. That is, if I have a map from an n-sphere to an n-sphere with the same degree, there would be homotopic maps. Mappings between manifolds of different dimension would be the next step in this development. The simplest case to examine would be among the maps from the 3-sphere to the 2-sphere, for which there was a particularly well-known map taking a pair of complex numbers to the complex line through the origin, and that point in C2. So that is, you can take, think of the 3-sphere as embedded in C2, and so you have 2 complex points for each point on the 3-sphere, and you map that to the homogeneous coordinates in the complex projective line, which is also known to be a 2-sphere. In his earlier work, Hopf developed the mapping degree of Brouwer, and so he was looking for a generalization for this case. Hopf associated to any continuous map from the 3-sphere to the 2-sphere an integer computed by choosing 2 points in the 2-sphere and considering their pre-images under this map, which are generally closed curves. The number he associated was the linking number between these 2 closed curves, which is now called the Hopf invariant. Hopf showed that if 2 mappings were homotopic, then their Hopf invariants agreed. Furthermore, the mapping that I gave earlier has Hopf invariant 1, and hence is not a homotopic to a trivial map. Finally, by analyzing how the Hopf invariant changes under compositions of maps from the 3-sphere to the 3-sphere or the 2-sphere to the 2-sphere, he showed that there were infinitely many different mappings from S3 to S2 that were not homotopic to each other. The importance of Hopf's paper cannot be underestimated. It opened up a whole new class of topological problems. At the 1932 International Congress of Mathematicians in Zurich, Čech gave a definition of higher homotopy groups of a space as a generalization of Poincaré's fundamental group. In the context of homotopy as a relation between mappings, we can express the fundamental group as a quotient of the set of loops, all loops where we identify 2 loops together if they're homotopic to one another. Loops are mappings of a circle to the space with a given point of the circle going to a chosen base point of the space. To generalize this, perform the same quotient on mappings of any sphere to a given space, where a given point of the sphere is taken to a given point in that space. Hopf's theorem detects the homotopy classes of maps from S3 to S2, showing that the homotopy group pi3 of S2 contained a copy of the integers. Čech's contribution, on the other hand, was just a definition, and was not only unappreciated at the time, but in fact, Hopf and Alexandrov advised that since the new groups that he had discovered were commutative, and that homology already posed enough problems for computation, that the new groups Čech introduced were uninteresting. Furthermore, Čech presented these new invariants without any applications or relations to other topological ideas. And so we get a kind of failure at that time of foresight by, in fact, 2 of the leaders of topology at the time, Hopf and Alexandrov. In a series of papers that appeared in 1935, rich in new ideas, Hurevich independently introduced the notion of the homotopy groups of a space, the higher homotopy groups of space. His definition was different than Czech's because it came with connections to the successful past of topology. Hurewicz, like most topologists of the time, worked on topological questions of a point set nature and combinatorial nature at the same time. His nth homotopy group of a space was the fundamental group of a topological space of mappings, particularly the mappings of the n-1 sphere to X. Hurewicz explored the point set topology of that mapping space and then applied the fundamental group to that new topological space and called those the higher homotopy groups. He was able to show, for example, that there were relations between these higher homotopy groups for a Lie group, a closed subgroup, and the quotient of the group by its subgroup. And with these relations, he was able to put Hopf's computation of the pi 3 of S2 into the context of the study of Lie groups. He also made one of the first steps in the development of fiber spaces. Hurewicz also related the higher homotopy groups to homology groups, the famous Hurewicz homomorphism. And finally, he introduced the notion of homotopy equivalence of spaces. Hurewicz had spread the news of his researches in a series of sketchy notes in the Dutch Academy proceedings. He also lectured on them at an important event in the history of algebraic topology, the International Conference on Topology in Moscow in September of 1935. This conference was organized by Alexandrov and brought together, quote, a large proportion of the active topologists in the world, unquote, according to Alan Tucker, a student of Lefschetz who had attended the conference. Tucker wrote of the meeting, the International Topological Conference held at Moscow last September showed that the subject has attained a definite measure of maturity and a wide range of influence on other branches of mathematics, but that it is still undergoing rapid growth and flux. What marks this conference as significant is the sense of a research community of active topologists that it represented. It was international, with participants from the Soviet Union, France, Germany, Holland, Switzerland, Czechoslovakia, Poland, and the United States. The independent discoveries of similar research paths brought mathematicians together, incited a flurry of papers, and set an agenda for progress in the subject. Leadership in the field was also clear with the attendance of Hagard, Lefschetz, Alexander, Alexandrov, and Hopf. 1935 was also important because two important texts were in topology made their appearance. 1934, there was Seifert and Threlfall's book on topology, and then Alexandrov and Hopf's book also appeared in that year. Thus, by 1935, the subdiscipline of mathematics, algebraic topology, had matured to the point where there was an international group of researchers working on recognized problems using shared methods. There were elementary accounts of the main ideas to introduce to new researchers of the activity, and active leaders like Hopf, Lefschetz, and Alexandrov to attract students into the field. The success of algebraic topology is due in part to the development it fostered in related areas of mathematics. Answers to questions in the foundations of analysis were found with new methods, and results like fixed point theorems led to new analytic ideas. Study of the fundamental group of knots and three manifolds led to insights about abstract groups, while homology groups presented a novel set of algebraic notions that later developed into homological algebra, in which the topological notions are imported to classify algebraic objects. However, this development was not smooth. There were false starts, difficult expositions, paths that looked to lead nowhere, and an atmosphere of change around the practice of mathematics. The anxiety of van der Waerden was overcome by the advances of Veblen and Whitehead. Of Hopf and Alexandrov, it was overcome by their own success. And of Weil, it was simply misplaced anxiety over a field which came to dominate the 20th century. So, now time, I'm going to stop there. Thank you.